As you can see by the big whiteboard, test is Monday. It's going to be set up similar to last time. I'm going to give you an hour to do it. Again, I'm going to take it. It's going to hopefully take me 10 to 12 minutes to do. I'll make it an hour for you guys. It'll be open from 8 a.m. to like 11:59 p.m. So you just have to find an hour sometime during the day to take it. And yeah, I don't have it done yet. I'm about a quarter to a third of the way through it. After this, I'm going to go record a an organic one lab. Yay. And then hopefully after that, I'll have time to work on it. My goal is to have it done sometime Saturday so I can send out a breakdown of what's going to be on the exam, just so it's like we normally would have. Someone asked me about how I'm going to do mechanisms. I have some options. So I could do something where like I do one of those like background pictures and you have to drag structures. So I like provide a bunch of structures and you have to drag structures and arrows in the right kind of order to make things work. It's one option. What I did in Organic 2 last semester is I put the steps, I like put like blocks of steps, like here's like a step or two, and then you had to like put them in order. And so some of the steps were incorrect because arrows were wrong or something. So you had to look at them and like figure out which steps you needed to use and then what order you needed to put them in. So, like the example I used in the early classes, like if the mechanism was this, right, you could have two blocks where one block is the bromonium ion and Br minus adding, and the other one was some like weird carbocation thing, right? And you'd be like, oh, I know this reaction doesn't make a carbocation, so I'm not going to use that as part of my mechanism, right? So through enough blocks, you could put it together that like, oh, it's block C, then it goes to block B, then it's block A, and then that's the mechanism, something like that. Or again, I could have you like drag structures into like a partially completed mechanism that are the right structures or something. I don't know. We're gonna figure it out sometime tonight or tomorrow. I'll be like, oh, this is the right way to do this. There will be naming. So if you forgot all the naming from the first exam, you're boned. Because that's just all the naming we have forever and ever. So do you not like that term? Boned? You boned? You're done. Um, right? So I'm gonna end up just having to add an extra layer of like now you're gonna have to do RNS on those things as well, right? So the way I can test RNS is to have you name things and then have you have the right stereochemistry associated with it. So yeah, I think those are the big test things. There is more matching, but this time I've already made the matching problem, or two of them, and instead of being 8 things with 24 options, it's 4 things with 12. It's 2 things of 4 and 12, so you have less to sort through. So hopefully that makes that a little bit easier. I literally met you halfway, literally halfway, just cut it in half. So hopefully that makes it a little easier to sort through as opposed to it being as big a block of letters to go through. So still the same number of wrong things, but just spread out a little bit. So hopefully this makes it a little bit better like on a technical side. So it's more about like what you know as opposed to like fighting with uh Moodle. Right. So hopefully that works out. Oh, and one more thing to help everyone out. If you want to go back and watch YouTube videos this weekend, because, whatever, the new stuff starts on slide set 3, slides 5 through 6, or 5-6. That is where that's the title of the video that the new material starts on. And it'll be everything to this video. So I'm going to try to get this video up as quickly as I can tonight. So, the other 20 people that didn't bother to show up today that aren't as cool as you guys, uh, they can actually watch it and not get totally dunked on when these questions show up on the exam. It's the one that starts with the Star Wars-esque crawl of text telling future generations that they don't have to watch me rant about exam one for 10 minutes. unless their exam score was below a 70, and then they have to watch it. But it's like if your class average is over a 70, go to like 1043 in the video. So that one. So you can relive that day in your life if you want to hype yourself up for exam 2. Be like, I can do better. You can like watch that and like listen to like Eye of the Tiger in the background and be like, yeah, get hype. Be great. Dun 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 dun. Be great. Okay. So another thing is all these reactions that we've done, I try to on the exam put at least one version in some way, shape, or form of every reaction that we've done on the exam. So I'm going to put one of each reaction somewhere on the exam. That is my goal. I just will go through the slides and go like, oh yeah, I taught that, and we'll put it on the exam. So I just start and I just go through. So expect to see one of everything on the exam, minimum. So I wanted to go over just like a quick review of some of the alkyne stuff that we did, or alkene stuff that we did on, what day was that? Wednesday. Twice now in 2 hours, I forgot what day we last met. Yeah, it's going well. 40, ladies and gentlemen, 40. Things hurt for no reason, and you can't remember days of the week. All right. And like, I can even say like I partied hard. I didn't do any of that. My brain has just turned to mush naturally. Can't be like, dude, I did so much blow back in the 90s. No, nothing. Yeah, like I just skipped like drinking and weed. I went straight to cocaine. Like I just skipped all of it. I was like, blow. I was just like, oh yeah. All right, so right, we're gonna take inside carbon to inside carbon. We're gonna put those together. Am I gonna make a cis double bond or am I gonna make a trans double bond? I got nothing but time. Cis or trans? It's literally a coin flip. It's what they tell you to get every SAT question down to. It is trans. I'm gonna pretend you said that with a lot of confidence. It is trans, 100% right. Right, so inside to inside. Right, Grubbs reactions always try to make the most stable double bond that they can, and the most stable double bond is going to be the trans double bond. When you have a symmetrical internal double bond, right, you just use half of it. So we're going to break this double bond in half and use one side and stick it to the inside of the other double bond. Know what happened? Oh, wait. Let me do this. Boop. We do this one. Sorry. I changed my mind. They're both secondary carbons. Make it hard to figure out which side gets what. So what would I do here if I have my double bond that I just made and I treated it with H2 palladium on carbon? You just get rid of the double bond. Right, we're not making any chiral center, so I don't have to worry about any wedges or dashes. Just get rid of the double bond. I go from alkene to alkane. I have an answer. What's up?
I was asked what the difference between Grubs 1 and Grubs 2 was.
For us, grubs 1 and grubs 2 are going to do the exact same thing. So if you see grubs and then a number, just you're going to do an olefin-metathesis. So there's no difference for us. So just treat them as being interchangeable. So what if we have grubs 1 at this time? So what would we make here? We have both double bonds in the same molecule. So generally when we do a metathesis like that, we make what? I'd make a ring, right? And so how big of a ring is we're going to count from the inside carbon of one double bond to the inside carbon of the other double bond. So we're going to have 1, 2, 3, 4, 5. So we're going to make a 5-membered ring. Right, and we're going to say that this one is the red one, and this one is the blue one. Right, so this will be, again, 1, 2, 3, 4, 5. Carbon 1 in our starting material has a methyl group, so carbon 1 in our product needs to have a methyl group. Carbon 3 in our starting material has 2 methyl groups. Carbon 3 needs to have 2 methyl groups. And what if I traded that with HBr, hydrogen peroxide, and light? Like we did that on that mythical day of Wednesday. Like you should be like right at the front of your mind. You should be like, oh yeah, this is super easy. I just learned this. The bromine, we're going to add a bromine, but since we're adding hydrogen peroxide and light, the bromine ends up on the least substituted carbon of the double bond. The bromine goes on carbon 5. If it was just HBr by itself, the bromine would go on carbon 1. So with the radical, we make the least substituted bromide. We make that. So So again, I'm going to make a ring. How big of a ring? 6 this time. I went 1 carbon bigger. So here to here, inside to inside, 1, 2, 3, 4, 5, 6. Like blue and red. Again, carbon 4 here has a methoxy, so it needs to have methoxy in the product. And if I add Br2 to that, right, I'm going to add a bromine to each side of the double bond. Are those bromines going to be on the same side, or are they going to be on opposite sides? They're on opposite sides. So they go, 1 bromine will be up, 1 bromine will be down. Right, so you remember the mechanism? you get to the bromonium ion, right? And then your other bromine has to add from the opposite side. So that bromine, the bromonium ion is blocking the top face the way I have it drawn, so the other bromine has to come from the bottom. So they always end up on opposite sides. So far, so good. So I'm going to start talking about alkynes. So we're going to do alkynes now, and this is particularly alkyne naming is going to be on the exam. It's just free money, but I get the alkyne naming on there. So, oops. So alkynes are molecules with a carbon-carbon triple bond. So you're going to have something that looks like, oops, this is an alkyne. One of the things that people have the most trouble with is counting the carbons in an alkyne. So this molecule here has 1, 2, 3, 4 carbons. Right, so people always seem to lose the 2 carbons that are on the triple bond. So this has 4 carbons. Right, so you're going to have a carbon. Oops. So it looks something like this. These carbons that are part of the triple bond, these carbons are both sp hybrid. So that means they took one of their s orbital and one of their p orbitals and mixed them together to make the hybrid orbital. And then they have 2 p orbitals on each carbon that aren't hybridized, that are just chilling out. The bond angle on an alkyne is 180 degrees. So alkynes are linear. That's degree C. Oops. Is that a temperature? Sorry. If you have an alkyne, the way I like to think about it, right, is you've got here and here, you have a pi bond, right? So just like an alkene, you have an alkene has a sigma bond and a pi bond. An alkyne has 1 sigma bond. Let's say the one in the middle here is our sigma bond, right? And then it has 2 pi bonds above and below that sigma bond. So if we look at the orbitals, how the orbitals are set up, you got your carbon and your carbon. You got your sigma bond in between them. We'll make it red again. Okay, there's your sigma bond. And then you've got 1 p orbital that is in the plane of the screen, right? And those p orbitals overlap, and they make your first pi bond, right? Now, the other set of p orbitals is orthogonal to this set of p orbitals. So they are coming out and going back. So then your green p orbitals overlap, but these are at 90 degrees from each other. So in a quirk of how electrons work, the electrons in the black orbitals don't know the electrons in the green orbitals exist because they are 90 degrees from each other, so they can't see each other. So there's no interaction between the green electrons and the black electrons. They're just hanging out blissfully ignorant that the other ones even exist. So that's basic structure. A fun little fact about alkyne physical properties is because they're linear, because that bond angle is 180 degrees, right? Alkynes have higher boiling points than similar, oh God, can't write today. Right, so they have similar, they have higher boiling points than similar alkenes or alkanes, right? And again, this kind of works out if you think about Tetris, right? Alkynes are linear. They're like the stick in Tetris. Super easy to stack them close together, right? You get to put a bunch of them together really closely. And so they have a lot more van der Waals interactions because they're closer together. They get more surface area contact. When you have an alkene, right, they're less linear. They're more the little weird S-shaped block, right, that are harder to stack together. And then alkanes, they're really wiggly, so they can take a bunch of different conformations. Think about all the different conformations you had, Newman projections, right? So it's harder to get them to fit close together because they're all wiggly. It's like spaghetti, right? They don't all fit together really. There's a bunch of like space for sauce, right? They don't stick together real well. So since alkynes are linear, they stack closer together. They're closer, they have more interactions, they have slightly higher boiling points. I want to stress again, always draw your alkynes straight, right? Always this, never this. We've all seen It's a Wonderful Life, correct? What happens when a bell rings? For the love of God. What happens when a bell rings in It's a Wonderful Life? An angel gets its wings. Thank you. Every time you draw a bent alkyne, somewhere a chemist dies. So don't draw bent alkynes. And someone's like, you just killed someone. I was like, yeah. One day it's gonna be me. I'm just gonna do it and be like, ah, and fall down. And my whole class is gonna go like, yes, we all get an A because he died. I'm emotionally traumatized. I don't even know if that's a rule, but you're all gonna say it is and be like, yes, today's the day. Step over my dead body to go to the dean of students. He died. I get an A. Drag my body behind you. I want my A. So, right, so always draw your alkyne straight. Or like on a test that you're doing bad on, you start drawing bent alkynes. Maybe this will get him. Is this the one? I'm not gonna pass this test. I need a way out. All right. So let's talk about naming alkynes. This is again like super easy money, right? You remove A and E from the parent hydrocarbon name and add YNE. So you go from an ane to an ine. And that's it. Other than that, you just basically follow all of your like alkene naming rules in terms of numbering and things like that. But it's super easy. So we know how many carbons that has, right? That has how many carbons? 4. So it'll be butane, because it's an alkyne, is butine. So it'll be but-2-ine. So what's the first one? Hexine. Yep. What number? Hex 2-ine, right? You need to make sure that you say where the alkyne is, right? If you just call it hexyne, then the alkyne could be anywhere, right? So you need to make sure you localize it with a number. Bless you. And now what's the bottom one? Octyne. 4 oct4-ine. Yep. Or 4-octyne. Yep. Seems good. Right? So we've got 1, 2, 3, 4, 5, 6, 7, 8. There you go. So 1, 2, 3, 4, 5, 6. Now, so here's where like remembering basic naming is going to come in handy. What would that be? No, so you've got to number it so the right, the alkyne gives you a suffix, so you have to number to give the suffix the lowest possible number. So we've got to number it in this direction so that the alkyne gets the lowest number. So it's going to be 1, 2, 3, 4, 5. So 5-methyl hept 1-ine. But the bad man put a wedge on the molecule, which means you have to do RNS now. So this is where remembering the naming from before is important, right? Because you've got to be able to do the base name and then tack the RNS on top of it, right? So is this going to be R or S? Let us see. This group is priority 1, 2, methyl is 3, hydrogen makes 4. The hydrogen's away from us. We connect the dots. So that's going to be S. Very good. Very good. The parenthesis around it, make it look fancy. There you go. So this is why like I can't really dress up the RNS problems too much. So having them like in naming where the name is something that you should already know how to do, and then with the RNS on top of it, that is how a lot of the RNS stuff is going to get done. So everyone good with alkyne naming? It's super easy, right? That's just like 6 free points on the exam. You're like, ooh, ane becomes ine. Pay me. All right. So per usual, I'm going to try to convince you that alkynes are interesting. Right, so I'll start with this guy. I forget what this does, but this is a pharmaceutical that like back in the early 2010, 2015 range made $163 million in sales for a year, and it has an alkyne incorporated here on the end. Now this molecule is more interesting, right? It's more complicated, right? So it's got this structure here that is an alkyne, an alkene, and an alkyne. It has this little 3-membered ring that has an oxygen in it. It's called an epoxide. It's some sweet organic 2 stuff. But so this part of the molecule, this part of dimycin, right here, its job is it goes and sticks the molecule between the base pairs of DNA, right? So if this compound gets in a cell, it finds its way in between DNA. And once it's there, this epoxide opens, shifts the conformation of the molecule, and makes it so this alkyne alkyne motif can make 2 radicals. They cyclize and make a ring, and they make 2 radicals, We've talked about radicals, so they're really reactive, right? So these radicals just start ripping hydrogens off of DNA. And then that DNA gets damaged, it gets cross-linked, like base pairs get stuck together, things get messed up. So now the DNA can't be read, or if it is read, it's read with a bunch of errors. And so whatever organism had its DNA all messed up dies. So this compound is teeny tiny biochemical warfare, right? So bacteria, funguses will make molecules like this and then excrete them. So then when other organisms come by, these molecules get absorbed, go mess up their DNA, and kill off the competition. So this is kind of like why we have penicillin, right? Penicillin is made by bread mold, so that when a bacteria comes by, the bacteria dies and doesn't eat the bread that the mold's on. Right? This is the same thing. So there's a lot of like aquatic organisms and stuff that make molecules like this that go in and damage DNA. We, like, other than this just like being kind of a neat structure, we use compounds like this made by organisms a lot of times as anti-cancer compounds, right? So like the reason chemotherapy sucks, long list, but is that they're super non-specific. They're just things that damage cells, particularly cells that reproduce quickly, right? Because cancer cells reproduce really fast. So we do stuff that like damages their DNA so they don't reproduce. If they try to reproduce, they break. That's why people's hairs fall out or they get ill, because the cells, your hair cells, your hair follicles, those are cells that reproduce quickly, and the cells in your gut reproduce quickly. So you're damaging those cells along with the cancer cells, right? But these are just little bacteria make these little like chemical weapons and send them out to kill other little bacteria or little sponges or whatever little sea creatures that come around, so they can kind of keep their little corner on whatever thing they're trying to eat or live on. And then we find them and try to make them and understand how they work. Right? Now, another thing, I'm going to break one of the rules I just told you, which is don't draw bent alkynes. The only time you're allowed to draw bent alkynes is if they're in a ring. Alkynes want to be straight, but you can put them in rings. The smallest ring you can put an alkyne in is a cyclooctane. And that in that ring, that alkyne is a little bent to make the ring happen, which leads to the alkyne being really straight. Why does this matter? So there's this class of chemistry that's been developed by Carolyn Bertozzi she's at Cal Berkeley, I do believe, or Cal Tech. You can't see her name. I swear, Carolyn Bertozzi, right there. And what she's developed is what's something called bioorthogonal chemistry. So they will take sugars that have a functional group on them called an azide, N3. It's a nitrogen double bonded to a nitrogen, double bonded to another nitrogen. And biological systems don't ever use this functional group. They have no use for it. We have no way of using it at all. So what that means is they can put these sugars, they can feed sugars to things. The organism will incorporate the sugar into their structures, and it'll have this tag, this N3 hanging off of it, that it can't use and it can't react with. Then they add this alkyne. And these strained alkynes that have these two fluorines here react with that N3 in the body, and then will stick a dye to that sugar. So you're able to see everywhere that organism incorporated the sugar. Normally, when you do something like this, you feed the organism some sugar, you then have to kill the organism to stain it so that you can see where everything went. But with this, because it's bioorthogonal, it doesn't mess with the biological processes, this dye is incorporated in an actual living organism. So this little C. elegans, this little worm, if you've hung out with Dr. Williams at all, I'm sure he has talked to you about C. elegans. They're his people, or his little wormy people, right? So they're able to take these worms, feed them sugar, and they can see where they incorporate the sugar based on what parts of the worm light up to correspond to the dyes that they give them. So they also do this with zebrafish. Zebrafish is like the stock biological like test organism. And what's great about zebrafish is they're see-through. So if you mess up part of a zebrafish, if you do something that causes a heart defect, you can just look at the zebrafish and go, oh, that zebrafish's heart's messed up. Oh, that's a normal zebrafish. Heart looks like that. This one doesn't look like that, right? But what they were able to do using this chemistry is on each hour or each day of embryo development, they could feed the embryos a different sugar and then give it a dye. And then in the finished organism, the different parts of the organism would fluoresce different colors. So they could see, like, on day one, we gave it sugars and dyed those sugars green. Those sugars went to this part of the fish. On day two, we gave them sugars and dyed those sugars red. These parts of the fish light up red. So they could track day by day which parts of the fish were being developed on day one, where those ended up. So it's like, oh, day one, we dyed stuff green, and now structures in the eyes are green. So, oh, the eyes, the things that develop first are the eyes. And they could go through and see what parts of the fish develop on what day. And you can do this all while the organism is still alive. You don't have to kill it to stain it or anything. You can just do it with the living organism. You can do it in mice too. Like you can make mice kidneys light up and stuff. So using these strained alkynes, you can do this neat chemistry and track stuff in living organisms. So again, back to the safety of the whiteboard. All right, cool. Okay. So I want to talk about some alkyne reactions, right? And we're going to do hydrohalogenation. Now, oops, try again. A lot of the reactions that we do for alkenes, there's an analogous alkyne reaction, right? So if you have an alkyne and you treat it with HX, you can add a hydrogen to one side of the alkyne and a halide to the other. Right, so if you take your alkyne, you treat it with HBr, you'll make a vinyl halide. This is a vinyl halide, right? You've got a double bond, and on the vinyl carbon, you have a halide, vinyl halide. There are two possible mechanisms to explain how this works. We're going to go over both of them, talk about some pros and cons. Right? So the first mechanism is almost the exact mechanism that we have for alkenes. And that is a vinyl cation mechanism. So you have your alkyne, treat it with HBr. Right? The vinyl cation mechanism is we're just stealing almost exactly the alkene mechanism, right? We have a pi bond, we have HBr, the pi bond adds to the hydrogen, breaks the hydrogen bromine bond. That makes a carbocation plus Br minus. That Br minus adds to the carbocation and gives you your product. This particular carbocation is a vinyl carbocation. These aren't particularly stable because carbons that are making double bonds are already a little electron deficient to begin with. So putting a carbocation on a carbon that's part of a double bond makes the carbon really electron poor. So vinyl carbocations are approximately as stable as a primary carbocation. So they're hard to form, right? So this isn't the best mechanism that we can maybe use to explain how alkynes react, because they make this really unstable intermediate. The other mechanism that's a little bit better is the pi complex mechanism. Here, again, same thing. We have our alkyne. It's going to react with HBr. And what kind of happens here is, instead of going full carbocation, we make this pi complex. We get our hydrogen effectively into just being really close to the pi bond, and it starts to weaken the pi bond. So I have this like partially broken carbon-carbon pi bond and these partially formed carbon-hydrogen bonds. That just weakens the pi bond enough that now our Br minus can add to that. And what ends up happening is your product. And this mechanism has two advantages. One, no vinyl carbocation, right? So we don't have to make that really high energy intermediate. Instead, we just have this hydrogen getting close to our pi bond and weakening it. And two, it explains the stereochemistry. In these reactions, your hydrogen and your bromine always end up on opposite sides, right? So the pi complex mechanism explains why that happens, because the bromine wants to add to the opposite side from the hydrogen. Not for sterics, but for electronic reasons. It wants to add to the opposite side, which is always going to put your hydrogen and your bromine on opposite sides. Now, if we look at an alkyne, how many pi bonds does an alkyne have? 2. Not a trick question. So in theory, our HBr could react with both pi bonds, right? I kept drawing a product where the HBr only reacts with one pi bond, but you could get a situation where you end up with no pi bonds in your product, where your HBr adds to both pi bonds. So how can we control if the HBr adds to one pi bond or if it adds to both pi bonds? And we can do this with equivalence. So, oops, how if I put a Q in that word? So equivalence is the ratio of starting material to reagent, right? So if you have one equivalent, you have a 1-to-1 ratio of starting material to reagent. So 1-to-1 mole ratio, right? 2 equivalent is going to be 1-to-2. Oops, 1-to-2. Right, you have one starting material for every 2 reagent. Right, so you have a 1 starting material, 1 mole of starting material, 2 moles of reagent. So if we look at a reaction, right, if I have one equivalent of HBr, so let's say that means I have 1 mole of HBr, and that means I have 1 mole of starting material. Again, not a trick question. That means we have how many moles of pi bond? 2. Not a trick question. 2 moles of pi bond. No, 2 moles of pi bond. So now I only have enough HBr to react with 1 pi bond, right? Because I have 2 moles of pi bond, but only 1 mole of HBr. So that means the product I'm going to get is going to be the vinyl halide, where I keep one of my double bonds. Now, if I do the same thing, but I have, instead of having 1 equivalent of HBr, I have 2 equivalents. Okay, so now I have 2 equivalents. Oops. That means I have 2 moles of HBr to my 1 mole of alkyne, 2 moles of pi bond. Right? So now I have enough HBr to react with all the pi bonds in my product, or in my starting material, right? So my product is going to have no pi bonds. This is going to be a geminal dihalide. Geminal is just a fancy term for on the same carbon, right? 2 groups that are on the same carbon, that's geminal. So why do the bromides end up on the same carbon? So we think about what's happening, right? You have your HBr, you have your first equivalent of HBr. It reacts with the alkyne, and what does it make? HBr. It makes a vinyl halide, right? Now that second equivalent of HBr that comes in to react, it's not reacting with an alkyne anymore, right? It's reacting with a double bond. So now it follows all the double bond rules, right? It's like, hey, I have to follow Markovnikov's rule. I put the hydrogen on the carbon that has the most hydrogens. I put my halide on the carbon that has the least hydrogens. So that means I'm going to put my hydrogen over here, bromide here, right? So you're comparing basically this carbocation versus that carbocation, right? Secondary carbocation is better than a primary. Bromines end up on the same carbon. We can just treat bromine like it is another substituent. So we can almost treat this as like almost like a tertiary carbocation. This is approximately similar to a tertiary carbocation because that bromine just acts as an extra substituent. So with that, I think we are done.